Hello. Good evening to all the participants here, and welcome to today's tutorial session. So this will be the weekly tutorial which will be conducted for our NPTEL course on urban utilities and planning, water supply, sanitation, and drainage. So as many of you would have already started watching the video lectures and might have started attempting the assignments and all that. So this tutorial session mainly looks at trying to solve certain questions, trying to discuss an interactive platform, because there's always this thing that most of the online sessions or online classes becomes one-way process and that interaction doesn't happen. So this is an initiative in order to merge that. And I am Jeslu Celine Jacob. I am a Prime Minister's Research Fellow in the Department of Architecture and Regional Planning at IIT Kharagpur, and I will be handling these tutorial sessions on water supply, sanitation, and drainage. So just to give a brief outline, which you already know, that this is a 12-week course, and every week you will have a graded assignment which you will have to submit in order to get your final certification, and finally you will have an exam also. So for every week we will have one interactive session that is like this, and this is the interaction session for week 0. So from next week onwards, we will have a detailed interactive session for 1 hour every week where we will discuss about what we learned during that entire week, and uh, what are the doubts that we have, and also we will try to answer certain questions. So after knowing the theory, at looking at solving certain questions is very important, and that is what we will focus on in these interactive sessions. And also, I'll just give a brief outline on how I've planned this interactive session to be so that we can take it forward very smoothly. So we will discuss certain questions. That is, today we're discussing about 6 questions. So we'll follow this particular format. That is, we'll take a question, we will discuss on that. I will give some explanation, and we will finalize on what is the answer. And after that, I will wait for about 1 or 2 minutes where you can shoot your doubts on that particular question, only on that particular question, nothing else. And those doubts will also be answered at that time. If you missed asking doubt for that particular question in that window, it's okay. You can put it in the chat box while we're discussing the next questions also. But I will only answer it towards the end of once we finish all the questions. And so as said, once we finish all the questions, again, we'll have a 5 to 10 minutes to discuss all your doubts on this and on any other topic which was discussed over the week. So I hope that is clear. So we'll have a discussion, a 1 minute gap for interaction, then again the next question, discussion, and finally, after we finish all the 6 questions, we'll have a detailed interactive session. So with that, let's proceed on to the first question. So the first question is, which of the following is an example of stormwater recharge structure? So for this, we need to know what a stormwater recharge structure is. Initially, what is stormwater? So stormwater is any water which falls onto the surface of the earth. So it could be rain, it could be snow, it could be any type of precipitation which falls onto the surface of the earth, and it is collected in order to recharge the groundwater, rivers, etc. So that is what we mean by stormwater recharge. So there are certain options which are given: vegetative swell, permeable pavements, infiltration basins, etc. So let's one by one see what these are. So what is a vegetated swale? So yeah. So vegetated swale is something where you have on the right hand side image, if you look, so you have some vegetation, and then you have certain pits or certain regions where the vegetation drops, or regions where water can be collected. So it can be in the form of a slope, and this slope is again filtered down, and this is what we call as a vegetated vegetation swell. So it's a swell which is formed, and the advantage of this is that it filters the water which is going down, and it also reduces the or increases the time at which the water goes down, so that it gives adequate time for the groundwater recharge structure, or the in order to hold groundwater. And in case the capacity of the groundwater recharge structure is not adequate enough to capture all this water which is coming through this whale, we also have certain pipes which will take this water onto the uh, nearby water body or nearby pipe. So this is what is shown in section. So this section, if we look from here, that is what is shown over here, where we have um, uh, a portion or a pit like this where all the water gets collected and it comes, and this recharges the groundwater. And if this if the capacity of the groundwater recharge structure there is not adequate enough, it goes through a pipe onto the nearby pipe. So this is a vegetated swell, and this has been taken directly from the presentation which is there in week one's lecture series. So you can refer to that if required, or if you feel that the more detailed explanation is required. So again, we are in a position to know that a vegetated swell is a very good example of a stormwater recharge structure. And the next one is a permeable pavement. So is a permeable. So what is a permeable pavement? So this is a good example of permeable pavement. We might have seen it in a lot of parking lots, walkways, footpaths, streets, etc. So where you have different concrete blocks, or you have instead of having an interlock block, you have gaps between them where there is soil and water can penetrate down towards that. So this is the permeable pavement. So what happens is that water comes down, and there are multiple layers by which water gets filtered and it moves down onto the soil. So here again, water gets collected. There's a groundwater recharge which is happening, and if the capacity is less, then it goes on to the nearby system. So this again is a very good example of stormwater recharge structure. And the next one is an infiltration basin. So here you have your ground moves to a place where you have the water getting stagnated in a region. So this infiltration basin, and then that water goes down and it comes onto the bottom. So this is again very much similar to that of swale, but here there's an infiltration which is also happening. So you collect, you filter, and then you take the surface runoff, you filter, and then you recharge. So as discussed, all these three are very good examples of groundwater or stormwater recharge structure. So the answer for this particular question would be all of these. That is, vegetated swell, permeable pavements, and an infiltration basin is a very good example of stormwater recharge structure. Now we move on to the next question on treated wastewater from sewage plants can be used for. So here, what is happening is that sewage water is not pure water. So we are using the sewage treated water. So it's treated again, so which means it doesn't have much impurities. We can reuse it. But the only place where we must not use it is for potable purposes. Why? Because this water does not have it's not pure enough to be consumed, or where you need potable water, this is not suitable. For all the other purposes it is suitable. For agriculture, where we need large amounts of water, it is suitable, and it's been done in a lot of places also, where using irrigation systems which are directly connected from the sewage treatment plants, water is being taken for irrigation purposes, and it's been very good also. It's the efficiency has been much good. And in if a industry use also, where you need large amount of water, it's used, and large scale construction activity also this is used. So this is uh, taken from the presentation which the professor discusses in week one lecture, where in detail the different uses of treated wastewater is being discussed, and at the same time how the state government or the different local bodies are using this treated water for horticulture, toilet flushing, etc., as a norm in their region is also highlighted, where under the head of Jal Shakti Abhiyan, it is a duty of these local bodies to ensure that the treated water is used for these purposes. So coming back to the question, it is used for all of these purposes. And now we move on to the next question on what is the per capita water demand for a hostel building according to IS 11721993. So what is IS 11721993? So basically, IS stands for Indian Standard Code. Any Indian Standard Code we have this IS notification, and these codes are very they are the simplified versions of these standards or the requirements that needs to be fulfilled in order to uh, give a particular service out or follow a certain standard for a certain industry practice. So it is there for anything, like IS standard codes are there for materials, for joineries, and now here for water supply. So this 1172, it stands for the IS standard code for basic requirements of water supply, drainage, and sanitation. So this is the standard code uh, which gives us the amount of water which will be required for certain purposes, and what is the quality of that water which will be required, how can we use it, where do we source it. All these details are given in this code, and the source of this code for interested students is given over here. So here I put a small screenshot of the code where it shows what is a water demand. So this is table one from that particular code, where the different demand for factories, hospitals, nurse homes, hotels, offices, restaurants, cinemas, etc. is given. And here we have our hostels, which is asked in this particular question. In hostel building, how much do we need? So we see that it's about 135 per capita, and it is per liter, like per day. So 135 liters per capita per day is required as per this code. So from this we get the answer for this. But the important point of this question is that you remember this code and you save this code, because this is going to be useful in the future. In this particular question, the code was mentioned, but sometimes the code might not be mentioned, and we ought to know which is the code that we need to refer to. Don't worry, by the end of this course, you will be able to understand what are the different codes that we will be referring to, and what are the different standards which are to be followed. So that is the whole idea of this course also. We need not memorize the exact value, just an average idea would be enough. But where to refer to when it is required, that idea we will definitely get from this entire course. So while you're referring to this particular question, this particular code, you can download the code and save it in a particular folder. Like, it's just a general advice or general thing that you can do. So let's move on to the next question on which of the following is used for population forecasting? So why do we need population forecasting in urban utilities and planning? Because you're designing utilities for a population which is not present right now, but for a future population. So it needs to consider on how the society would be, what will be the developments in the next few years, so that whatever we're designing doesn't become redundant in the next year, because a huge amount of investment is being put in this particular utility that we are planning for, and it is not for that particular, it is not limited to that particular time, but it is for a future population also. So in our week one lecture, we are discussing about the different population forecasting methods. So there are different methods such as mathematical methods, then economic methods such as the cohort survival method, employment ratio method, etc. So here in the mathematical method, we have arithmetic increase method, geometric increase method, incremental increase method, logistic curve method, and graphical method. So these all these methods can be used, and it's like progressively this incremental increase method is the best method which is used in mathematical methods, and arithmetic increase method and geometric increase methods are also used. So in arithmetic increase method, it's basically if you have 100 people about 20 years before, and 10 years before you have about 200 people, and currently you have about 250 people, then this increase is about 100 people, and this increase is about 50 people. So your overall increase which is happened over time is that you have about 150 people has increased over the last 20 years, and it has happened in 2 decades. So in 1 decade, the average increase is about 75 people. So you take this average value, and if you want to know what will be the increase in the next decade, you put this average value. And this here I've taken only about for 2 decades. If you take it for around 10 decades back, how it would be, we would be more or less be able to get an average growth progress which is happening. So the idea is we are looking at historical growth in order to predict what will be the future growth. So that is what is happening in all these mathematical based methods. And in geometric increase method, again, we are saying that there's a rapid increase which is happening in the population. So we look at a geometrical increase, so we have the initial population as P0, and then we have the average geometrical rate. So again, we're taking an average geometrical rate, that is, if every year, what is the geometrical rate of increase which is happening, we are averaging it, and then we're looking at the number of decades. So the unit we are using here is decade for the number of years, because we're not interested to know within 1 year or within 2 years how much of population is growing, but we're interested to know over a large period of time how much people are growing, because our whatever we're planning for will be planned for a long duration. So that is about geometric increase method. Again, the major assumptions behind these mathematical models is that there is no other nuclei, or there's no other special element which is happening, like the growth is happening exactly how it happened in the previous years. If there is a new industry which is come up, or if there's a new town which has come up, then the or new attraction which has come up, then the whole method, population forecasting method, using mathematical methods fails. We need other economic based methods. So mathematical method has this assumption that no other external factor is happening within that region, but it is the normal growth by which the region was growing. The same growth continues to grow. And then we have the incremental increase method. So in here in geometric and arithmetic, we discussed that it is only the average growth which is happening every year, that average growth is taken, but what if the variation which is happening every year is vastly different, then averaging that will not give us a good idea. So we take into consideration the rate of change of increase which is happening in each decade, that is every time. So here there is 100, and then that 100 becomes 50. So basically there's a 50 people are reduced. So there's a reduction in 50 people over time. So which means that next year also probably there would be a reduction in people which is happening. So if you look at a pattern for around 10 to 20 decades on how it's happening, what is the increase or reduction in the rate of change of population change, that also plays an important role. So that is what is dealt in the incremental increase method, where you have the initial population and you have this rate of increase for each decade. At the same time, you have this rate of change in increase for each decade. So this is the formula. How to do the calculations in detail, we will discuss in the future tutorials, where we will take up an actual problem and we will try to solve that problem. So again, to answer this particular question, all the three methods, arithmetic increase method, geometric increase method, and incremental increase methods, are used for population forecasting. So now we move on to the last question for today, that is, what is an aquifer, and what is an aquifer? So we discussed about stormwater recharge structure. So in that we saw how filtration is happening between the surface and the groundwater. And why this filtration is required is because whatever stormwater or surface level water that we are getting is impure. And this impure water is not good. It has several impurities, and it's not good for consumption or other purposes. Whereas groundwater, when we use, we want pure water, like that would be much easier for us to use. So aquifers actually help in removing these impurities from the surface water and recharging our groundwater with good pure water. So that is what an aquifer is. So here I'm showing certain images of aquifers, where you have a certain surface level water, and then you have certain filtration units through which the water flows and it aquifies. So this is an example where you have water in a particular pond, and then it gets filtrated and it goes. So it's a set of rocks or a filtration units through which the water flows before it reaches the groundwater is called an aquifer. So to answer that, it is A, where a body of saturated rocks or soil through which water can easily move is called as an aquifer, and the purpose is that it filters the water in the process and it recharges the groundwater. So that's all about the questions for today. So now if you have any doubts, you can raise them and I will be answering them. Okay, I think there are no doubts. So if that's the case, then we will meet next week with more questions. And in between, if you feel that you have any doubts, you can always drop it in the discussion forum, and you can quote this particular session that we had, week 0 session. I will be answering them over there, or I will either type it them. If it's a simple one, I'll type it them there, or I will take it up during the next tutorial. So have a nice evening, everybody, and good night. See you next week.